going on? Today we're going to be looking at just the same stuff as yesterday. Going to be researching the M1 GPU, potentially for purposes and contributing to Asahi Linux in a few months. Let's get into it. So we left off talking about triangles. Nothing crazy. We were kind of hitting a split between this and this. I left off here on rasterization units. So let's continue. So 1 sec. Let's continue here. Bruh. Alright. We have rasterization units, texture samplers, render output units, and other bits which work together with shaders. Turn the triangles from the app to the screen. So we said that rasterization units figure out which pixels a triangle covers. Get a bounding box, walk over the pixels, decide if the pixels are in the triangle, generate fragments, output fragment cores. Texture samplers fetch textures from memory. Handle filtering, bitmaps, addressing modes, have their own hardware texture. And render output units are the final step in the frame buffer. Alright. So what is a command processor? Let's see. It's a command processor that takes drawing commands from the app and sets up the shader cores to process them. This is going in the other direction a bit. This includes data like what list of triangles to draw, what global attributes to use, what textures will be used, what shader programs to use, where the final image goes to memory. Then sends this data over to the shader cores and other units to program the GPU to actually do the render. So command processor takes drawing commands from, the dispatcher and a state machine that translates. Okay. I think that's a good. Command processor is a dispatcher state machine that translates calls from Vulkan, OpenGL. What was the other one that was referenced? Metal to GPU work. Alright, sits between the CPU and the app. Oh, it switches between the CPU and the GPU execution units. If the app sends a draw something, it doesn't send triangles directly, it sends commands like draw, mesh, shader, textures, uniforms. These are APIs like Vulkan, OpenGL. The driver composes into command. What the command processor does, reads command buffers. Alright. Oh my gosh, I'm on the wrong screen. My bad. Greeks work into stages. Okay. How it fits into tile-based GPUs, instead of just streaming work through the tile-based context, it helps organize work into tiles. So, just look at the image. GPU command dispatch unit, read buffer, size and offset. So the offset is where it exists in the memory mapped user buffer. That's fine for now. Important subtlety, it's not just a sender. Programs the whole GPU state, schedules work, controls ordering dependencies. Closer to a lightweight operating system for the something like Asahi Linux, this is one of the hardest parts. Apple's command format is undocumented. Right, so satisfied there, and you have a memory management unit. So a memory management unit, which is in charge of limiting the access to memory areas belonging to a specific app, so apps can't crash. It's like a virtual mem for GPU. Holy message. So it's like virtual mem for GPU. Without an MMU, you could read each other's textures. You could overwrite the operating system. Yeah, so gives each app a virtual address space. So define app. Is this process? Is this thread? Is this OS allocated? Like, what is an app? That seems imprecise. with the driver. So that's why graphics drivers are difficult. Makes sense. So you can have multiple contacts. It's a GPU level context, not a thread share. Okay. So back to the top here. So when a shader accesses memory, it's using a pointer and translated from memory. That shader's on purpose, so it's isolation. TLBs. Virtualize different hardware paths. File-based tile memory on chip often bypasses normal virtual memory. Everything else, texture buffer, still goes through the MMU. Unified memory on Apple systems. So I think I'm fine there. I think I trust that the memory management unit is doing that. So in order to handle all of these moving parts in a reasonably safe way, modern GPU drivers split into two parts: user space and kernel driver. User space compiles shader programs and translates API calls into GPU command lists. Meanwhile, the kernel part is in charge of managing the MMU and allocation, deallocation from different apps. So it's deciding how and when to send their commands to the command processor. All modern GPU drivers work this way. Custom API that is customized for each GPU family. UAPI. UAPI. So what's the user space part? Ask the kernel to alloc dealloc. That means in order to make the M1 GPU, you need a kernel and user space driver. All right. Let's learn a bit, or teach me about M1 Asahi kernel versus user space drivers. Available GPU components. Kernel versus user space. Let's also just quickly see how this looks like on localhost. Did my tmux resurrect? Bruh. tmux resurrect is not working, bro. My work config is better than home config at this point. M1 GPU. Memory management unit. So this is also not as zoomed in as I like having it. Forces process cycle isolation. It's like virtual memory for GPU gives each app a virtual address space. All right. So kernel. Kernel space owns mu. This is like manage GPU vmem, set up page tables, which is kind of the same thing as managing GPU vmem, allocating buffers, enforce ISO. And you got command submission. What is that? Accept command buffers from user space. Validate. Send to GPU. Schedule is here. Which processes run on GPU? Yeah, that's implied by scheduling. So handles interrupts. Power management. Blocking. Translation. So when your app says draw a triangle, Mesa turns it into. That's my arms falling asleep even like below the heart here. Mesa turns it into GPU understandable commands of shader compilation. Yeah, that's crazy. That's actually super cool. That's something I'd like to look at. Command buffer building. Resource management. So the app calls draw mesh. Uses space driver, compiles the shapers. That's command buffer, allocates the resources, prepares everything. Kernel driver receives the buffer, validates it, maps it, submits it. GPU executes command, Tyler, output. Design is intentional for encapsulation and firms. Smaller, easy to trust, use so you can crash. An update mess. Okay, yeah, that makes sense. Faster iteration. Important for reverse engineering performance. Reynolds lane. So app and GPUs are undocumented tile-based and very different, so Asahi had to figure out MMU format, implement some mission queues, handle faults. Reverse engineer command encoding, write a full compiler. Yeah, the compiler is crazy. Map, OpenGL, upload GPU behavior, where earlier concepts fit. Everything we discussed bugs here. Command processor driven by command buffers building user space. Tile-based rendering controlled via commands. Mesa generates MMU managed by kernel driver. Shader cores execute compile shaders from Mesa. One subtle but important detail: the kernel does not understand graphics. It doesn't know traders triangles. It only knows memory buffers, command streams. All graphics is in the user space. Yeah, so let's look at how Mesa compiles shaders for Apple GPUs. So I'm gonna wash my hands real quick. Let me also put some on the G. Dinner today, we got some almonds. Coke Zero, no caffeine. I really wish they would release a Dr. Pepper no caffeine product. I'd buy that. All right, let's go back to the cause. So yeah, how does
Mesa.
Mesa, me, me, me? Sure, Mesa. Mei. I feel like it can't be a. That diphthong for one letter doesn't make sense. This is some classic compiler optimizations here. Kind of dope. I don't like that. They make it look like a link, and then you click it, and it opens up another element. I don't want to do that. Lowers NIR to Apple-style operations. Vector ops or scalar ops. This seems like the largest simplification of all time. Vector ops, map them to scalar ops, just like where the size of the vector, I guess. I also wish it wouldn't jump down, because like obviously I'm gonna read the rest of it. Reg allocation, where values live, how to reuse them. Instruction selection, abstracts ops into real GPU instructions, so here you have a mole that's mapping to ADX mole. Instructions are weird often, so scheduling. So Mesa, you have the shader compiled by Spur by application. Then you might have this in Vulkan or OpenGL. You have the AST to the IR to another IR to another IR. The LLVM for these drivers for Radeon and LLVM pipe. Curious, I think that's a bit out of scope, but I appreciate the image regardless. This is crazy. I was trying to figure this out. This is what I was gonna ask. Like, how do you special instructions? Texture sampling, interpolation, derivatives from MIP mapping. Also, what's MIP mapping? Apple GPUs are picky about float formats, packing, alignment. Yeah, that sounds brutal to reverse engineer. NIR. NIR is a universal bridge between front ends like GLSL Vulkan and back ends AMD Intel Apple really. So Asahi didn't have to build a full GLSL compiler, only NIR to Java GPU. That's cool. subtle but deep. Compiler isn't just translating it, it's adapting it to a massively parallel execution model, a tile-based architecture, a very specific instruction set, so it's doing math translation, architecture mapping, performance optimizations all at once. Sweet. A barycentric interpolation. So these are like separate things that I'll look at afterwards. Because like that could be a whole one of these, but we need to finish this post first. So vector ops and scalar ops. Vector op is working with vectors back A, B, C, A, B, summing the individual components. So you can do it by using native vector. So is this related to SymT in the ArcImp? Let me see the yes or no first. Yes, kind of. So maybe, okay. We can also do it with scalar hardware, which is what Apple GPUs do. So it's just, this is faster and takes up less space, I guess. The compiler has to back C, it decides, do I keep this as a vector op or break it into scalars with the hardware scalar? Okay. Why do this? It's powerful for better scheduling. You can reorder non-dependent ops. Avoid a wasted work if only the part of the vector is needed. Float. Also, let me make sure this is on. Should we increase the bitrate? How do we do that? File settings. Output. The bitrate wants to be 25,000 kilobytes per second. That's crazy. I feel like it used to be like 1,000. That's a lot of data per second. This is 1080p. Wait, are we shooting in 4K? This looks horrible for 4K. That's the thing with 4K, like if it's 4K but you compress it down to 10% like lossy compression, like is it even 4K at that point? Yeah, man. Might as well get our money's worth out of YouTube. Alright. So you can also avoid wasted work if you don't use all the components of the vector, you can just do one computation. Sure, matches hardware exact model. A lot of GPUs like mini scalar instead of one big vector. The images are a bit of a stretch every time. So in MESA, it happens. GLSR, NIR, scalarization happens from NIR to back into machine code. NIR has bad. Okay, how do you? Okay, I'm just gonna say NIR. Breaks vectors into scalar, simplifies ops. Then the Asahi backend maps those scalar ops cleanly to Apple instructions. So it seemed like there was. I'm a bit confused by this because they were just saying that the breaking of vectors into scalars is dependent on the underlying architecture, but they also made it seem like NIR is like agnostic of what backend you use. I'm surprised to see this in the NIR section because I thought you just said that uh, the NIR is agnostic to the underlying backend, but the breaking of vectors into scalars depends on the backend. Is that accurate? Jump to that real quick. NIR is designed to be backend agnostic, but it includes optional passes like scalarization that are enabled based on backend needs. It does not assume a specific one, but it's flexible enough to target them. That's all I need. So back to where we were. Yeah, the scroll, it really needs to be like a tree, not just one massive line of text. Because, yeah, I'm scrolling up halfway back up the page at this point. Alright, that is wild. This wasn't guesswork, it's a very systemic process. Started on Mac OS. Feed inputs into Apple's stack and observe outputs. Ran apps, wrote small shaders, captured command streams. When an app uses Metal, Apple's API, the system builds command buffers. Sahi devs intercepted those, dumped binary command streams, recorded associated stages and researches. got Wireshark for your GPU pipelines. Controlled experiments, then just look at random data that designed experiments. Change one thing in a shader, capture GPU output, and change it again and compare results. Now you know which parts of the binary correspond to constants and how values flow through instructions. That's really cool. Differential analysis. Take two nearly identical shaders, diff the compiled binaries, what changed and why. This reveals instruction encoding, or register usage and control flow pattern. Build a mental model of the ISA. Over time, they figured out instruction formats, register files, execution models, special ops. Not from docs, but from patterns. No, that's super cool. Write a compiler to match it. And I feel like you could brute a lot of this using LLMs. Not to be a shill, but that is curious. Writing power to match it. Once you understand it enough, take NIR, generate instructions, run them on real hardware. If it works, great. If not, refine model. Got it using model, not in AI context. Validate with your ops, final test, run actual workloads, game test, benchmark, compare. Should correctness, performance, edge cases, visual. No. Treat it like a function. And for its implementation, sure. Especially hard because you had to figure out instruction coding, bits to ops, scheduling behavior, mem model, tiling, sync. Had to be correct, certainly. What is bit mapping? Related to texture sampling. When you map a texture onto a surface far away, what is distance in this case? Far away, texture shrinks. When you map a texture onto a surface far away, texture shrinks. What is far away in this case? What do you mean far away? Copy this for the Control F, refind. The texture covers a small number of pixels on the screen. Does not mean the object is far from the camera in 3D space. It means the texture covers a small number of pixels on the screen. How many screen pixels? Imagine a checkerboard close to camera. Checker might cover 50-50, lots of detail. A big texture gets squeezed into a few pixels. The textures, pixels. After one screen pixel, you have to pick or average them. So that's what aliasing is, and that's noisy patterns. Far away means it's being shrunk and like transformed. GPU estimates how fast UV coordinates change. Not gonna lie, UV in my head is ultraviolet. What's UV? Okay, it's like the vector positions within a texture. Yeah, okay, that makes sense. So determines, so something can be far away in the mid mapping sense. It's far away. It's far away because the pixel depth of the texture and its orientation are different from that of the render target. Okay, so let's go back to this. Up one. Up one. I copied this from. Huh? I copied this from. What? There's no way this is the only instance of this because I copied it to Control F and get back to where it was. Bro, this is so corny. Is it up here? No, I hate the unrendering stuff. That's really annoying. So you just gotta ask a massive train of questions, and if you want to copy something, Control F back up, you can because it's unloading. Oh my god. So MIP mapping recomputes smaller versions of it. They're in subsample. So I can't tell a difference, I'm not gonna lie. So that's texture filtering. Yeah, not gonna lie, could not tell the difference. How it works at runtime. When sampling a texture, GPU estimates how big the texture peaks on the screen, picks the appropriate MIP level. Okay. That makes more sense. Even better are blending levels. Instead of picking between one level, pick two and blend between them. GPUs like Apple's, it reduces memory bandwidth, improves cache efficiency, and makes textures look stable. See, I want to ask, like, oh, does this improve cache efficiency because things tend to stay the same size in you're like in adjacent times or adjacent frames, so you have to load a smaller thing on average. But if I ask this, I'm gonna have to go halfway down the page, and then this isn't even gonna be rendered anymore. Excuse me. Is there a way to do that? I know, like, honestly, the Claude Code interface is better for that. Happily. Uh, the mapping use lower resolution textures when things are far away to avoid wasting and save work. Final takeaway: Asahi shader compiles or exists because they need a reconstruction of the entire GPU. Derivatives. That starts to make sense with 3D stuff. So native vector hardware. Problem is, if I click this, I can't get back to the question, bruh. Related to SimT, vector versus scalar is about instruction shape. SimT is about how many threads execute instructions together. So I was curious, like, if these are meta instructions that in the architecture is like what SimT is. Orthogonal modern GPUs deliberately combine scalar instructions with SimT. Single instruction multiple threads popularized by NVIDIA. So if you click this, it's a chat thing that's like, oh, what is NVIDIA? Like, for such a waste. Many threads run the same instruction at the time on different data. How is that even a novel? I feel like the utility of this implies that they're using the same data, or else it's just the same as any other processor that has three. Instead of one, like 4, process 32 out of 64 threads, each doing scalar work. But then it is like the same data. Eh. So VecCB. So you could use vector hardware, which is one thread on 4 components. Or you could use 4 threads at each. Okay, that makes sense because they're independent. Modern GPUs replace wide vector instructions with many parallel threads because of better flexibility, better structuring, and less wasted work. Avoid wasted lanes. Handles divergence better because of code branches. SimT can mask threads and run paths separately. Let's see how vector can't do that in the same way with branch prediction. That's inevitably what this is doing as well, but alright. Better hardware util, instead of one wide ALU, you get many small ALUs. Easier to keep busy, that is reasonable. Executes a wave or a warp of threads, 32. Each thread runs the same instruction, each thread has its own registers. Yeah. Sure. All right, so I think we're caught up. So somebody named Alyssa joined the project. Drawing a triangle with open source code. That's super based. How am I getting rate limited on GitHub? My home computer I just got on an hour ago and I've loaded the site twice. And where's my dark reader, bro? Holy shite. It actually aids. So, not that for now. So, she did it on Mac OS. That makes sense. Dude, my arm is like tweaking. I can't really feel it. That's crazy. So there's a whole ARM64 CPU coprocessor running an Apple proprietary real-time OS. Really? That's curious. Handles power management, command scheduling and preemption, fault recovery, and even performance counters, statistics, and things like temper management. In fact, the macOS kernel doesn't communicate with the GPU hardware at all. All communication with the GPU happens via the firmware using data structures and shared memory. There are a lot of them. Initialization data is used to configure power management settings in the firmware and other GPU configuration data, including color space conversion tables. 1,000 fields. Color space conversion tables? Is this for like color blindness or something? Vertex renderer commands which tell the vertex processing and tiling part of the GPU how to process commands and shaders from the user space to run vertex part of the whole render pass. Fragment rendering commands which tell the rasterization fragment part of the GPU how to run or child vertex data from the vertex point of the frame reframe. Curious. Pointer to a micro sequence of smaller commands that are interpreted by the GPU firmware. Firmware literally takes the same page table base pointer used by the GPU MMU, configures it as an ARM64 page table. The GPU memory is firmware memory. The shared kernel address space, similar to the kernel address space on the, which is what the firmware uses for itself and for most of its communication with the driver. And then some buffers are shared with the GPU hardware itself and have user space addresses which are all in separate address space. Chat. That's making sense. But can we all move this complexity to user space and have it set up all those Vertex fragment rendering commands? Nope. Since all these structures are in the shared kernel address space together with the firmware, and they have tons of pointers to each other, they're not isolated between different processes using the GPU, so we can't give apps direct access to them because they could break each other's rendering. This is why OS found all those rendering details in the Mac OS API. Okay. GPU drivers in Python. Since getting all these structures right is critical for the GPU to work and the firmware not to crash, I needed a way of quickly experimenting with them while I reverse engineered things. Thankfully, the Asahi Linux project already has a tool for this, the M101 Python thing. And so I was already writing a GPU tracer for the M101 hypervisor and filling out the structure definitions in Python. I decided to flip it on its head and start writing a Python GPU kernel driver using the same structure definitions. Python is great for this since it is very easy to iterate with. Even better, it can already talk the basic RTKit protocols. So that's curious, and I improved the tools for that so I can see exactly what the firmware is. Set up our scripts on a development machine which connects to the M1 machine via USB, so you can reboot it every time you do something and the test cycle is very fast. At first, most of the driver was really just a bunch of hard-coded structures, but I managed to eventually get them right and right and trying. Damn. That's ridiculous. Go up. I'm not trying to edit it. I'm trying to go up. Where's my Vimium? Hello? Oh my god. Here I'm Shim. It's cool that that worked. Yeah, that's hellish. So this is why they're using Rust. That's actually curious. That's not what I was trying to do. That's curious, Rust. This is crazy. The first Linux Rust GPU kernel driver. Okay. The person that wrote this is Hoshino Lena. Is a VTuber.
Because it's one. Oh.
There it is. KMS Cube. I mess with KMS Cube. Really? A few days later could run a full GNOME desktop session? Really? That's ridiculous. It's a plus 568. That's wild. Race conditions, memory leak, use after free. Just didn't happen. Yeah, go-to cleanup is disgusting, I'm not gonna lie. Yeah, the go-to. You will be curious to see over the next like 20 years how system software it ends up being written, especially like the LLM stuff. Because all this stuff where people are just saying, yo, LLM, find bugs in X, does seem like a lot of those bugs won't be logic bugs, but stuff like this person mentioned race conditions, memory leaks, and use after freeze. Quake in, this is incredible. Quake in 4K. All from KDE. So Ella is working on something. So I think I need to set up an IRC client on like a VPS. Which I'll do off stream because I don't want to expose my private keys. So, let me finish these last paragraphs before I start talking. I'll subscribe to this person on YouTube. Sure. Sean. They still make videos. Let's see. 8-hour stream? Damn. Packaging Python.
The random rabbit hole.
Yeah, I have no idea what you're working on, dog. I'll still subscribe for the culture, out of respect. Alright. So, I think that's going to be this here. So let's look at it. Excuse me, sorry. So I'm set aside with that. Let's get that out. Alright, so what is next? I learned a bit about the GPU, a bit about its context in like M1 tile-based stuff and Asahi. I think what's next is that's highest util for like getting back and working on it is just kind of reading around the code base and honestly getting into the IRC chats. Should probably do that. I might. So it's 8:12. Still got a few hours. How long have I been doing this? Been doing this for an hour. So I'm gonna stand up and walk around for a minute. Oh, let's make a new one of these. Not based on this. Let's duplicate this. Saying like stepping outside. That might not be the best verbiage. How do I want to say this? FK. FK, I guess. All right. So I want something like this text here, basically, on top of here. Let's also do something like BSOD. Copy BSOD cursed on top. That's not good though. And then on this one, let's do like a. Is it linking all these? Yes, it is. So linking all of those. Let's just throw. Let's throw a FreeBSD image. Throw background. Why do they all have backgrounds? This one looks a bit different. So save. Can you not save an image in 2026? What the hell? Bro. We have ask an AI chatbot about an image before you can save an image. You're actually fucked. This one's like 8K with a background. Oh my god, dude. The problem is I'm using Bing. Wait, I already have that? Bro. Probably the same exact image. Alright, let's get BSD image. BSD. BSG, sure. BSG. 5526. Sure. Let's go here. Let's filter that image mask on like a blue. Make it a blend. Let's make it a. Now we can blend mold. That looks good. Heart emoji. Looks a bit cursed, I'm not gonna lie. Try something else. Let's try cat. It's cat. No. Oh, where do you go? Sure, let's do this. Let's do text. John text. Back soon. Sans serif is fine. Back soon. I forgot to copy it. No! Oh wait, here, okay. So in text, remove from there. Rename this one. Back soon. Rename this one face. Alright, back soon. Fake. All 4K. Why the What's on the slot? Pretty nice. Alright, so I'm gonna use this to conceal. Let's also make this smaller because it's just kind of annoying. So we're gonna use this to conceal IP while I go and do my I2P thing. And I need to get my Tmux stuff. So I really miss having that. Sure love this song. Holy left ear. Is it? Do I unplug it? No, it's this far left ear. How did it just go to the left? What the? What the? I plug my headphones in the left ear. Why? What the hell? My headphones just broke as. I stand up and my headphones just broke. I've never heard of that ever. Dude, what? I stand up and my headphones are just broken. In the 5 seconds it took to stand up. This left ear shit is pissing me off. I can't imagine what happened when I put down my headphones. I picked them up and they just don't work anymore. Because it could be this cord in between them. Last thing I need right now is to buy new headphones, dude. Heard this track in another set already. Taking a long ass time. Dude, are these broken? Go copying paths. Having very slow networking right now. Rage baitish. But I'm just gonna make sure I don't leak anything. So we're copying Nick's paths here. Let's read something else. Let's chat what to read. Turn on memory. So copying these paths. Parts 2 to 3. Or is there parts? One of the parts. What are the other parts? I'm gonna go. This is taking eons, bro. I shared a valve. That's actually dope. An hour based shader compiler. Helix. English, French, Spanish. It's pretty dope. Based for learning language. Go copying paths here. Dude, why did it remove the text on the whole component, bruh? Oh my god, I hate that. That is actually so annoying. Why is... That's so funny. Dude, my left ear loves this track right now. Oh my gosh. Is it? This is actually freaking bad. Definitely the other way around. Dude, it's in my left ear. What are we doing? I refuse to believe that my headphones just broke. They're just unusable. Oh, that's very annoying. That sucks, dude. The day's work is gone. Let's fix this. Oh my god. Selecting. Should be fine. Let's go back to this. So I think it's a lot. It's reloading. Sage into. So it's restarting. Hopefully it's not crashing. Still not up yet. Okay, it's just not coming up at all. Yeah, I gotta redo my whole config. Storage. Damn, that's so. That's broken and my headphones broke just immediately. Beautiful. Doesn't work. So this was useless. I'm just trying to find what part 2 it says. Read part 2. And Michael, what is part 2? Part 2 is dissecting the Apple GPU part 2. So is this gonna. Alright, so you gotta do that. Alright. So let's read this. Disassemble simple shaders with a simple and shout out Lima. Pre-critical calls are memory alloc, command buffer create, and command buffer submit. Or at all bit sizes. That's one. Two. Bulk of the new code is responsible for constructing the various command buffers and descriptors resident in shared memory. curious. So by doing things from their smallest parts, especially when you have all these magic numbers and just random shit, makes it easier to progress without having to debug all your numbers. Hmm. Copy the last entry. So the first entry, just copy it to the last and then swap. It's curious. Okay. Holy based website. an alternative to LVM. We wrote AMD something, really? Instruction set AGX2 has Go arithmetic, vector input output, 16 byte types, free conversion 16 to 132, free floating point absolute value. Really? 256 registers. Register usage thread outputs you can see trade off. Conform multi-issue or superscale execution. Each hardware property induces a compiler property. Scalar sources don't complicate the compiler by allowing unrestricted vectors. Vector values of the periphery separated with I don't understand that. 16-bit units. Sources and destinations are sized. Old size conversion instructions and uses. Absolute value negate bits. Okay, so that's how it's immediate. A large register file means running out of registers is rare. Yeah, I did notice 256 is so you don't care about register spelling. Minimizing register pressure is crucial. SSA forms ops. Scheduler simply reorders instructions without leaking details to the rest of the backend. Doing is feasible both before and after register log. Putting it together, designed for an AGX compiler, merges the code generator, translating an error to an SSA-based intermediate representation, optimized by instruction combining passes, schedule to minimize register allocated while going in SSA scheduled again, maximize instructional power, and finally tagging bonus. Okay. These descriptions reflect the hardware traits specific to software, which are themselves shadow skips with hardware. Investigating these traits offers some to hardware itself. Consider the register file can access to the 256 F4 registers. There's a performance penalty. The more registers used, the fewer concurrent threads possible since threads share a register file. Makes sense. Number of threads allowed in a given shader is reported in metal as the max total threads per thread group product. We decided the register per thread returning and study the register pressure versus occupancy. Okay, by varying the register pressure of metal shaders. Correlating. Okay, so 1021, and I guess like 1 to 1ish. That threshold, it doesn't really matter how many registers. So that threshold is well. No. Yeah, that's fair. It's crazy. It's 5 megabytes of register file. That's ridiculous. My fan is causing something to bump against something and it's annoying. He more active on GitLab now. I hate how sensitive that is. But I'm glad. I'm actually impressed that it drags back that one. Alright. So it's a 5. 6. 7. 8. Just to N. Not an ML. So maybe just go to 8. Oh, it's a 7. Maybe we're on 3. Sorry, we're on 4. Let's kind of verify our knowledge here. Alright. So let's read 4. It's kind of making it seem. GeoX gears. Does this person get invited to work on this? Like, how does that work? Seems like if you're hiring this person or like some random intern, like, huh, should be encoded with 0. Yeah, that makes sense. Based. All right. Rebuild the whole system without looking. What happens from draw call to pixels on screen in the M1 GPU? What happens? So, um, what happens? Let's think here. So the draw call is converted into a series of a lot of intermediate representations. The most critical one on the Apple side is LVM, but on the Asahi side or Mesa side is NIR. This NIR, hmm, specific level. Problem does tiling solve? Solves a few problems. It's mostly for optimization, so perhaps it doesn't solve an exact problem, but you could say the problems are just like the constraint of power and space and speed. Tiling is useful because it divides the screen into tiles, which allow graphics shader cores to operate on tiles, which is useful because it allows unchanged parts of the screen frame to frame to not have to be re-rendered. You have to re-render something if a triangle that's order box lays on a tile, you have to render it if something on that triangle changed. And so if this tile is the whole screen, you got to re-render the whole screen. Whereas if the tile is on a, if the tile is smaller, you only have to re-render it and process for that tile. And that can work because the memory is mapped from the tile to the frame buffer in a memory controller. Okay. What does the command buffer actually contain? The command buffer contains so I'm just gonna try to answer these questions. Or I already answered the first. Let me just do it. Wait, great parts of the screen. Is that not what I said? Oh, it's not doing that. It avoids writing intermediate results to main memory during a single frame. Really? The screen is split into tiles. Geometry is binned into the tiles first. Each tile is rendered completely. Only the final result gets written out. So the win is massively reduced memory bandwidth. It's a memory thing. Good clarification. So the command buffer, yeah, I was kind of guessing on that. They're not shader instructions. They're not shader instructions. They are. The command buffer is built by the CPU or the driver, contains things like run the shader, uses buffer draw, and vertices. GPU drop description that compiled from NAR, GLSL, NAR, and machine code, executed by cores when the command buffer tells them to. Command buffer is the script, shader is the code that runs inside the script. Shaders run on GPU cores, correct but incomplete. Firewire interaction. Vertex shaders run during geometry processing. Fragment shaders run per tile. That's clutch, I didn't know that. Vertex shaders run during geometry processing. Fragment shaders run per tile after tiling and binning. Execution is grouped SymDCT-like. Fragment shaders don't just run whenever, they run tile by tile after binning. Yeah, that makes sense. Why reverse engineering is needed? Correct but shallow. Undersells the difficulty. Formats are known, memory layouts known, synchronization are known, hidden firmware behaviors. Oh, these are unknown. Yeah, I get what I was saying. It's more like you're trying to talk to a machine where you don't know the language grammar or rules the conversation. Not just setting the right flags. I mean, you can't just write drivers because you're not going to even know what to write, is what I was trying to say. Not sure. Fine version. CPU builds a command buffer after describing GPU work. GPU firmware parses it and orchestrates execution. Geometry is bent into tiles. Each tile is rendered fully in fast local memory. Shaders compiled via massive pipeline run during this process. Final fixes are written out once per tile. Why does tiling specifically fragment shaders more efficient? Why does tiling specifically make fragment shaders more efficient? Because tiling allows for the parallelization of vector instructions to scalar instructions in the M1 across shader cores. That's incorrect. Damn. Tiling isn't about enabling vector to scalar execution. That the machinery exists regardless of time. So this is wrong because parallel shader execution already happens on any modern GPU. Whether the ISA is vector or scalar is independent. Tiling doesn't change. It's all about memory. Tiling doesn't change how the instructions are parallelized. It changes where the data was last state. So I'm mixing execution model, SIMD, gene scalarization with memory in the rendering strategy. The reason tiling makes fragment shaders efficient. Data locality and bandwidth reduction. Without tiling, fragments are shaded as they come. Immediate results are written to main memory. The same pixel is shaded multiple times. I don't understand that. Why does breaking it down make it where there's a less memory usage? Why do you have to draw it less times? What trips to main memory during heavy overdraw? Depth stencil tests happen before shading. Many fragments never run the shader at all. Intermediate blending. Result is within once per pixel. Tiling doesn't reduce how much you compute. It reduces how much you move data, and on GPUs, moving data is often the bottleneck. Bonus nuance. The design is why Apple GPUs care a lot about tiled memory size. That's why structure workloads. It's why they structure workloads around render passes. That's why they behave differently under heavy override. Try finding your answer in something like tiling improves. I don't understand what's memory. The GPU determine visibility before running fragment shaders. was I was already reading this properly. Where do shaders actually get invoked in the command stream? Command buffer doesn't contain shader code. It contains references to shaders and tells the GPU phases. Shaders go through a pipeline like GLSL, NAR backend compiler, not to the Apple GPU machine code. That compiled code gets stored in GPU accessible memory. The command buffer just points to it. Right, let's see if my sound is fixed. Still left. Very annoying. Shader program when you reach this stage. Vertex shader builds a tiles, fragment shader runs within tiles. You bending without expensive shading or rejection of hidden fragments, running fragment shaders only when necessary. Find shaders. Time when you draw a call. Okay. Reordering the pipeline so visibility is known before shading happens. Makes sense. Hmm. Yeah, that makes sense. Fragment depends on the current pixel value already in the frame buffer. Blending forces ordering because each fragment's output depends on the current value of the pixel, so fragments must be processed in sequence rather than in its parallels. Opaque rendering is parallel because visibility is a selection problem. Transparent rendering is hard because it's a composition problem. Order independent transparent. Yeah, linguize in the GPU is ridiculous. Yeah, accumulating the weighted color in alpha is kind of cool. Back in. I need to like um oh you did. Hmm. I've been muted for years. So I don't really know what I'm doing, but theme is just the color of the text. Actually, not bad. It's kind of cool customization here. This is a cool way to customize this. But yeah, this kind of culture is different. Okay, wait, please go away. This kind of culture is definitely curious, and like I don't really know if I like it, or I actually kind of don't think I like it, cause like We just go to this. Like there's a ton going on. Yeah, I'm just gonna end it here. Yeah, we'll see what else we're gonna do.